Oh, by the way, in this solution with Jupiter out there, slightly tugging,
Right. Yes.
it turns out over a very long time scale, this is chaotic, but much longer time scale than Newton ever imagined.
Okay.
Okay? Because, yes, we are small compared to the sun, but Jupiter isn't, all right? And we're trying to orbit between them.
Here, we're talking about how a simple rule, gravity pulls on gravity, creates a future that is knowable in principle but slippery in practice. When you add one massive neighbor to the sun, the equations didn't get harder, they changed character. Two bodies trace perfect ellipses forever. Three bodies start sharing energy and angular momentum in ways that no single formula can capture. And when one of those bodies is Jupiter, 318 Earth's worth of pull, the subtle becomes significant over time. The headlines here are not about sudden doom. They're about timescales and subtlety. The inner planets, including Earth, have what we call a Lyapunov time of a few million years. That's the time over which two nearly identical solar systems, differing only by the thickness of a human hair and a planet's position, drift so far apart that their futures are effectively different. Newton's laws never change, but tiny nudges, asteroids, thermal forces, mutual tugs get amplified. We can predict eclipses centuries ahead with confidence. Extend that to tens of millions of years, and individual orbits become a blur of possibilities. If the equations are exact, why can't we know where Earth will be in a billion years? Because exact equations don't save you from exponential sensitivity. There's structure in the chaos, and that's the key. Mathematicians call it CAM theory. If the gravitational tugs are small, many orbits remain locked on quasi-regular tracks. But at special ratios, resonances, the tracks develop cracks. Take the asteroid belt. There are missing bands, the Kirkwood gaps, where an asteroid would circle the sun 3 times for every one of Jupiter's orbits, or 5 to 2, or other simple ratios. In those zones, Jupiter's nudge repeats in sync, pushing the rock's orbit until it's ejected or redirected. That's not random. It's geometry doing work over time. Resonance can also protect. Pluto's elongated orbit crosses Neptune's path on paper, but in reality, they're in a 3.2 resonance. Every 3 Pluto years, Neptune completes 2, and the timing ensures safe passage. The Trojan asteroids ride ahead of and behind Jupiter at Lagrange points, gravitational parking spots where the pulls balance just right. Even the volcanically tortured surface of Io is a testament. Io, Europa, and Ganymede are locked in a 1-2.4 resonance that pumps Io's interior and keeps Europa's subsurface ocean liquid. But stability in one corner can mean instability next door. The same resonances that preserve can also pump up eccentricities and tilt axes elsewhere. These long-term nudges don't just redraw orbits, they modulate climates. Earth's ice ages are paced by Milankovitch cycles, changes in eccentricity, axial tilt, and the orientation of our axis that adjust how sunlight is distributed across seasons and latitudes. The eccentricity cycle, around 100,000 years, is strongly influenced by the combined tugs of Jupiter and Saturn. Precession, roughly 23,000 years, depends on those tugs too. Over millions of years, because of chaos, the exact timing and strength of these cycles drift. The broad pattern remains, but the beats evolve. Compare Earth to Mars. Mars lacks a large stabilizing moon. Its axial tilt can wander chaotically between small and very large angles over millions of years, transforming its climate. Earth's moon, oversized by planetary standards, damps our tilt into a narrower band, keeping our seasons within a predictable range. In that sense, our moon doesn't just make tides, it locks in a climate friendliness that chaos might otherwise erode. And if orbits can reshape climates, they can shape histories. Now, fast forward billions of years. Numerical simulations, most famously by Jacques Laskar and colleagues, show that Mercury's orbit is the most precarious. Its eccentricity can wander so high that, with a small probability, it could collide with the Sun or Venus in the distant future. The odds of catastrophic changes for Earth are tiny on those timescales, but the uncertainty is real. It's important to distinguish chaos from catastrophe. Chaotic doesn't mean doomed. It means our predictive power decays with time. The system appears long-lived. Current simulations find no likely route to ejecting Earth before the Sun's evolution dominates, though it can't be ruled out in principle. But small interactions accumulate, and beyond the horizon, the details blur. Look outward to other planetary systems and you see the same rules play out with different outcomes. Many stars host hot Jupiters, gas giants parked scorchingly close to their suns, likely migrants that spiraled inward through interactions with gas disks or other planets, destabilizing inner worlds along the way. Others form resonant chains, like TRAPPIST-1's 7 Earth-sized planets, arranged in a delicate interlocking pattern that advertises both order and a hair-trigger sensitivity. Tip 1 ratio, and the whole chain can rearrange. So, are we lucky, or are we typical? We might be both, untypical in that gravitational systems straddle order and chaos, lucky in that ours landed in a configuration that nurtures long-term habitability. And here's the twist. We've learned to use this structure, not fight it. The Voyager missions rode a once-in-176 years alignment of the outer planets and used gravity assists, those very same energy exchanges, to tour the solar system. Modern mission design exploits the Interplanetary Transport Network, a web of low-energy pathways traced by unstable manifolds near Lagrange points. It sounds abstract, but in practice it means we can surf the subtle contours of gravity, spending less fuel because we know where the currents flow. That's a practical philosophy for living with chaos. You don't demand an exact forecast for the position of every molecule of air next month to know that winter is coming. Weather is chaotic. Climate is predictable. Planetary positions billions of years hence are weather. The existence of resonant structures, stability zones, and statistical tendencies is climate. We aim spacecraft, plan calendars, and model ice ages by leaning into what remains predictable while respecting the horizon where precision dissolves. So the lesson isn't that the universe is unknowable, it's that knowledge has a domain. We have laws that are exact, and we have systems that amplify small differences. Between those two realities lies our responsibility to measure carefully, compute honestly, and plan cleverly. The giants in our sky don't just threaten to scramble our predictions, they give us the tools to move through space, to understand our past climate, and to imagine futures that are plausible rather than assured. We're not the center of the solar system. We're not even the main characters in its long-term dynamics. But we are the species that notice the difference between certainty and reliability and learn to thrive in that gap. Like if this was interesting, and hit the subscribe for more.